everyone, this is Mrs. Jackson. This is Chapter 4, Section 2, Part 2. And in this section, we're going to talk about something called work rate problems. And it ties directly to one of the essential questions of the chapter. And that is, how do we model real-world problems where we have different people working at different rates, and how to analyze that situation and figure out how much time it will take to get a job done. Okay, so the key concept here is a term called work rate, and that's just a generic term that we use to describe multiple people, multiple robots or machines, inanimate objects all working together at different rates to get a job done faster. And when I say working together, I mean really simultaneously at the same time. So to start out with, I want to show you how to actually break down a word problem of this type and how to set it up with a mathematical model. So this first example, we have two inanimate objects, two hoses, filling up a swimming pool together. Now it takes a long time to fill up that volume of water. So in this scenario, they're working together. They can complete the job in 15 hours. One hose, however, is 3 times faster than the other hose in terms of volume output. And the question is, how long will it take the slower hose to fill the pool by itself? So we don't know how much time it takes the slower hose. So we are going to assign a variable. So hose 1, the slower hose, we're going to say by itself, I'll just say alone, takes X hours. And the faster hose, hose 2, again alone, we need a model. And our inclination at first might be to describe this as 3x hours, but that would actually mean that the faster hose is taking more hours, in fact 3 times the amount of hours to fill the pool by itself. So hopefully that would highlight to you that we want 1/3 x hours. In other words, it's faster, so it's going to take 1/3 less of time. And then together, we're told that they can fill the pool in 15 hours. Okay, so one method here I'm going to write is hose 1, slower hose, plus, so in other words, if they're working together, that would indicate the operation of combination or addition. So we've got hose 1 plus hose 2 equals some result together. The word rate should indicate to you ratio. So we usually use ratios to describe rates, and a ratio is a fraction looking quantity where we're kind of comparing two different units. In this case, we have pools and we have hours. So for hose 1, the slower hose, I'm going to say it fills 1 pool in X hours. And hose 2 fills the pool in 1/3 that time. An easier way to describe this mathematically would be to say that it can fill 3 pools in X hours. And together we're told that they fill that 1 pool in 15 hours. So I want to just point out to you that notice all the pools, the unit pools are all on the numerator and the hours are all on the denominator. So this is key whenever we use rates of any kind in any mathematical model, that when we set up a proportion or ratios, that we're consistent. So the tops have to be all the same units and the denominators have to be all the same units. And I just noticed that I forgot hose 2 here, so put that 2 there. All right, so that's one potential way to model. And as long as we're consistent, we could do the reciprocal of that. So in other words, I could say that hose 1 in X hours fills 1 pool, and hose 2 in X hours fills 3 pools, and in 15 hours together, the 2 hoses fill 1 pool. So in other words, I completely took the reciprocal. As long as I am consistent with units, all hours on the numerators and all pools on the denominators, these are mathematically equivalent. Upon inspection, however, one, in my opinion, is preferred over the other. So in this case, we have a common denominator right here, X hours. So to add fractions with a common denominator, we simply add the numerators and keep the denominator. Whereas here, I mean, it's not going to be a lot of work, but here we don't have a common denominator. We would have to rewrite this fraction with the equivalent of a denominator of 3 pools. So in my opinion, this top model here would be preferred. It just simplifies things a little bit. So I had not intended for us to solve this problem here, but we might as well. We've got 1 pool over X plus 3 pools over X, so I can combine them. So let's go ahead and do this. So we've got 1 over X plus 3 over X equals 1 over 15. I've got 1 plus 3 over X equals 1 over 15. 4 over X equals 1 over 15. This is actually an excellent opportunity that I would use the reciprocal property of proportions. In other words, we could put X over 4 here equals 15 over 1. You have to take the reciprocal of both sides and cross multiply. So X equals 4 times 15, which is 60. And remember, X is hours. Specifically, it's hours of hose 1 working by itself. Hose 2 is 3 times faster. So remember, for this particular pool, it would be 1/3 X, which would give us 20 hours. So hose 2 is going to take 20 hours by itself. Hose 1, 60 hours by itself. Together, of course, they get the job done faster, and together they can get it done in 15 hours. All right, let's try something a little bit more rigorous. And we're going to layer in some complexity, which is money. Okay, so most of the time in real world, when we're talking about work rate problems, we're really making business decisions, and that's about time and money as well. So in this particular scenario, I'm a homeowner, you're a homeowner, you're looking to have your fence painted, and you have 2 teenagers in your neighborhood that have given you some pricing. So the first situation is that Samantha is 17 years old. She paints twice as fast as Jack, who is only 13 years old. Together, they can get the fence done in 12 hours, and they're going to charge a combination rate of $200 for the entire job. Working alone, however, Jack will charge $5 per hour, and Sam will charge $12 per hour. So the scenario is posed to you. Are you going to hire them as a team? Should you hire Samantha alone? Should you hire Jack alone? What's the better deal for the homeowner? All right, let's break down this problem and see what are the important numbers here in this particular scenario. Sam and Jack's age, that's irrelevant. That has nothing to do with time or money, so I'm not going to highlight that. But I do see that together they can get the fence done in 12 hours, and they will charge $200 together. Working alone, Jack charges $5 per hour, and Sam charges $12 per hour. Also, Sam paints twice as fast as Jack, so that's also important. All right, so I'm going to start trying to put a mathematical model together. I've got Jack working together, so that means addition, with Samantha, and they equal some kind of time frame together. I don't know how many hours it will take Jack alone, but I can say that Jack will get one fence completed on his own in X hours. And Sam works twice as fast, so I could say that she could get 2 fences done in the same amount of time. And together, they're getting 1 fence done in 12 hours. So when I inspect my model, I see that all of my numerators are fences and all of my denominators are hours. And that's what I'm looking for. I need consistency. To solve this, I could multiply everything through by 12x if I wanted to. But since I have a common denominator here on the left, I might as well add them together. So I have 1 over x plus 2 over x equals 1 over 12. I have 1 plus 2 over x, since I have that common denominator, equals 1 over 12. 3 over x equals 1 over 12. Another great opportunity to use the reciprocal property of proportions. So I could take the reciprocal, x over 3 equals 12 over 1. Cross multiply, and I have x equals 36 hours. And remember, that is Jack's time alone. So it would take him 36 hours to complete this fence on his own. And it's going to take Sam half the time. So that will take Sam 18 hours to finish the fence on her own. All right, so now that we know how much time it would take them alone, let's try to do a little business model here with the dollars. So I am going to say, I'm going to make a little table, I think is probably the easiest thing to do. Let's say Jack alone, Sam alone, and together. So in terms of time, we just said, or we just calculated, that Jack would take 36 hours and Sam is 18 hours. And together we were told in the original problem it would take them 12 hours. Now let's layer in the money. So in terms of price per hour, I guess Jack is kind of underselling himself, I think, only charging $5 per hour. Sam is charging $12. And so if I multiply $5 times the 36 hours for Jack, that comes out to a cost of, to me as the homeowner, $210. Likewise, Sam, 18 hours times $12 per hour would come out to be $216. And together, they gave us a proposal of $200. So clearly, in this case, this is what I would call a no-brainer here. They're going to get the job done together in 12 hours, and it's the cheapest cost. So as the homeowner, the fence owner, I'm clearly going to choose door number 3 here. I would suggest that Jack and Sam kind of mess this up. They should have done a little math and charged much more than the $200 for the total job. As a homeowner, time is money, as the saying goes. If they're going to get the job done in only 12 hours, I probably would have been willing to pay upwards of like $250. So I think that their business model kind of undersold themselves a little bit, but clearly in this case, faster and lower costs, I would definitely go with them together. All right, so in this video, we talked about a key element of the entire chapter, which is work rate problems, and how we would use these types of rational expressions and rational equations to model real business scenarios. Anyway, hope this video helps. Thanks for listening. Please subscribe.